So today we have two big news. We have Jim Fan and Yuk Ju, who is the co-founders of NVIDIA's Gear Lab, which is embodied AI. They've dropped yet another video explaining a lot more closely exactly what their lab has been able to accomplish and what they're doing. We're going to watch that. We're going to explain everything. And then, of course, another big humanoid bot dropping another video, which is 1X, this time their Eve. But what's really cool about their demo is that they actually show how they can package a cardboard box together, not just pick and place, but actually filling it up. So I want to show you that later as well. So welcome, Scott.
Hello, Herbert. I thought these were just only going to be weekly affairs, and here it is only Tuesday.
Daily affairs. All right, so let's watch this. So yesterday we saw the NVIDIA conference. Jensen Huang came up and talked about these humanoid bots that they're working on. And then Jim Fan, who is the founder of the NVIDIA Gear Lab, which is their embodied AI group. And he said this: 2024 is the year of humanoid. There's no robot hardware, more general purpose. We are all in. The humanoid is going to be a big deal. They're supporting these bots. And then Yuk Ju, who is a co-founder of the Gear Lab, along with Jim Fan, he dropped this video. We'll watch this now. And that explains a lot more than what we saw yesterday. The Project Root, a general purpose foundation model for humanoid robots. So this is their foundation model that they will allow all these different vendor partners to be able to use. It will enable the robots to follow natural language instructions and learn new skills from human videos and demonstrations. So we'll watch that. I'm going to go ahead and play that. It's a 3-minute long video. And then what we'll do is we'll come back and explain each part as we go along.
Over the past decade, NVIDIA has made massive leaps in robotic learning, in simulation, and the real world, including Vima's multimodal prompt learning, Dexstream's highly dexterous manipulation, Automate's diverse assembly solutions, Animal Parkour's adaptive mobility, and Isaac Manipulator's novel object pose estimation, grasp identification, and real-time dynamic motion planning. Now, building on years of groundbreaking work, it's time to reimagine the mind of humanoid robots. Researchers at NVIDIA are working with leading innovators in the robotics ecosystem to create NVIDIA Project Root, a general-purpose foundation model for humanoid robot learning. The group model takes multimodal instructions and past interactions as input and produces the next action for the robot to execute. We developed Isaac Lab, a robot learning application to train Groot on Omniverse Isaac Sim. And we created Osmo, a compute orchestration service that coordinates the training and inference workflows across DGX systems for training and OVX systems for simulation. With these tools, we can train Groot in GPU-accelerated simulation and transfer zero-shot to the real world. The group model will enable a robot to learn from a handful of human demonstrations. The robot could then help with everyday tasks, like cold pressing juice. And it's not just repeating the training data, it's recognizing its environment and predicting what to do next to achieve its goal. A robot powered by Groot can learn generalized skills like coordination and dexterity that can be applied to a variety of helpful tasks. And emulate human movement just by observing us. This is made possible with NVIDIA's technologies that can understand humans from videos, train models in simulation, and ultimately deploy them directly to physical robots. Connecting the group model to a large language model allows it to generate motions by following natural language instructions.
Hi, GL1. Can you give me a high five?
Sure thing. Let's high five.
Can you give us some cool moves?
Sure. Check this out.
With Isaac Lab, Osmo, and Groot, we're providing the building blocks for the future of AI-powered robotics.
So very similar to the video we shared yesterday, but at least this time around, they actually explaining a little bit more. What did you think, Scott?
Yeah, it was nice to see some of the background and some of the narration to fill in some of the things we were saying and maybe confirm what we had, and then anything we're a little bit wrong to get that corrected. And also, remembering that NVIDIA's had sort of a long history in this arena already. Way before the humanoid bots are trying to solve other set of problems in robotics, and that's why they have such a powerful toolkit, because they're just building on top of the experience they already have, and that doesn't hurt to already have a lot of experience in your pocket to know what it is your vendors are going to need and understand exactly what their needs are and building on top of it. And it also seems that everyone really wants to partner with NVIDIA. So usually you see these partnership announcements like, oh, 2 or 3, so they can say, use the plural on partners, but 10. And they were like, all the big names save one. And we know which one that is, because that one doesn't need to partner with anyone. That's Tesla. But all the others need to. And they're coming on in there. And I think they probably are very willing to do it, because I don't think NVIDIA plans on ever building their own humanoid bot. They'll probably be happy to just have the, kind of the brains of the bot, but they'll let the robot chassis be developed by anyone else who wants to do it. And of course, that's the same thing, in theory, Google is not competing against the phone manufacturers, but they did kind of come out with a Pixel. So you got to be a little bit careful. So I'm assuming they do not have any plans to come up with their own. And that's why it makes it a lot easier for others to willingly go in, share their data, give them an idea of what's going on. And they just need to learn how all these different humanoid bots are working, so they can provide the tools that are going to be needed. And it's exciting to see that lab. I mean, it reminded me a lot of like a humanoid bot preschool, seeing everyone there going in with the instructors, kind of showing them what they're doing, teaching them how to walk and do these other very simple tasks.
Sounds good. All right, let's take a look at the video again. This time we'll break it down into parts, and you can explain a little bit more to us. This is, again, Yuk Ju saying that the generous robots need a versatile body and an intelligent mind. The NVIDIA Gear Group, led by Dr. Jim Fanemy, is working closely with the partner robotics companies to develop robot foundation models. So these robot foundation models, I'm assuming, is what we're going to see here.
Yes.
Each one separated, simulation, teleoperation, just watching, these various ways to teach robots, with the goal of deploying millions of general purpose robots to real world tasks.
Right. Now, notice the very interesting choice of words there are the generalist robots. Typically meaning, like a humanoid form, but doesn't mean there couldn't be some other formats in there. But as we've been saying all along, the idea of the humanoid bot is to be general purpose, not to be specific. In order to do that, you need to have a versatile body that can do a variety of things and is just not specific to a particular task. Yes, there will be specialist bots that will be much better than generalists at doing one task. They won't be able to do a wide variety of them. So you need a versatile body that can adapt to that environment. But most importantly is you need that intelligent mind. That's where the versatility really comes from, is the fact that you have an intelligent mind that can adapt to everything that's going on. And I guess the other thing to point out what Jim Fan said is, like, 2024 is the year of the humanoid bot. I'm like, oh, so I guess it's no longer the year of the dragon.
Yeah. Good one. There's a part in that video that we're going to watch that I thought was very, very important, where he said it's not that they didn't just train the bot and it's like copying what it does. That's one thing. It actually understands its environment. It knows.
That's the whole point.
That's a lemon, or that's a glass. This is, the machine, and this, like it knows. So let's watch this, and then you can tell me to pause, or I'll pause, and then we'll break it up into little pieces here. But so I'm assuming this is all simulation, right?
Yeah, this is simulation they've done in the past. You may remember there have been a lot of examples of these humanoid type of hands to do like the Rubik Cube and other things like that, where you need to have a lot of simulation capability in there to be able to develop that kind of dexterity.
Let me just pause for a second.
Yeah.
Yes. Just it says here that this is a digital twin, and then there's the real robot. Could you explain that a bit?
Yes. Okay. So I think OpenAI also did something similar. I don't know if this is the same hand or not, where the Rubik's Cube would end up being solved by a robotic hand. And in order to do that, you needed lots and lots of training data. And it would just take forever to do it on the real one. So you need to have a simulated environment to get an idea of exactly how it's going to work. Now, it's a really tricky problem because there's a lot of physics in there. It's everything about the contact points, where they are, what you have to do to be able to move it around, especially when you're doing a Rubik's Cube. This is a lot easier, just doing a manipulation of a cube, but a Rubik's Cube where you're trying to get everything to spin around, that is something else. And doing it with one hand, for a human, it's hard enough doing it with two hands, and you try doing it with one and figure it out. And that was an amazing thing that OpenAI did. And we're seeing sort of the same kind of thing there of trying to develop dexterity through the simulation. So you need to have a really good digital twin to simulate everything that's going on. And once you get enough training data, you can now start to deploy to the real world. And when you bring it to the real world, it might be okay. And then you need to do a lot of training in the real world to get it right, because your physics may be off a little bit, or your model is not quite right, and you need to tune it for that. But the idea is to get these models better and better so it works right out of the box. So you can make all those mistakes, you can do all the possible combinations and train them in the simulation really quickly. It takes a lot longer to figure that thing out in the real world, or to do those runs in the real world. And that's what they are talking about coming on up here. And there's like lots of other interesting things are going on back there with, dynamic collision avoidance and everything, which is already something else. So that was just traditional robotics, and now bringing it into the humanoid space and realizing how they can kind of accelerate what they've already been able to do in this other robotic space to now the humanoid bots. And training data is going to be key. We know that with FSD, the more the cars drive, the better FSD gets, because it needs more and more examples of what it's like to do driving. Same thing with these different tasks. You need to see these different kind of robotic tasks and to be able to plan what the bot is going to be able to do, or let's say, do all the training and testing in your virtual world before you go ahead and deploy. And the better you can do, the better it's going to behave the first time. That's they refer to like one-shot training. So they came up with an example of what they want the bots to do. They go through and they simulate it numerous times to be able to understand its environment. And so it's not that we are keeping the glasses and everything exactly in the same location each time. That's very easy, because the bot can basically close its eyes and pick it up. The idea is that it recognizes certain objects and knows what it has to do. And so you can place those things differently and it will figure it out, even though it's never been trained that specific task exactly the way it is. And
so that's what they mean by one shot.
That's what I mean by one shot, is they've done all the training.
So much in simulation, but when you do real world, one shot, it can do it.
Yes, even though even though the world has been randomized at that point.
Gotcha.
So you get some randomization there. It's a kind of task. Maybe it's something like, a cleaning task, picking up the glass and wiping it down. You train it and train it and train it, and you train it in enough different positions and orientations in simulation that when it sees it in the real world, it knows exactly what to do, even if the position of that glass in the real world is not exactly the way it has seen it before. It's just like, oh, I know how to interpolate that and figure out what I need to do to be able to do it, and it'll do it the first time. And so if you can do that in one shot without having to go and have it knock over the glass a bunch of times and then gather more training data and then have to retrain. So the goal is to always get it to be as close to one shot as possible, because then those things are just gonna be ready to go. And that at this point, all you have to do is just start training all kinds of different conditions and situations that the bots will be able to do almost anything, even though they've never seen it before. Yes, there will be things that the bot won't be able to do because no one imagined it doing that particular task, and it hasn't seen anything remotely close to it, and it'll be stumped. Same with humans. I mean, we could do a lot of things, and if you suddenly handed me a musical instrument and say start playing, I'll be like, I don't know. It's not on my data set, okay, my training set. So it's going to be the same thing with the bots, is that you're going to be showing it lots of things that are going to be factory operations. You may be showing it things in the home or something like that. But if you suddenly say, okay, we want you to do carpentry today, if it hasn't seen anything like that, it won't be able to do it. So you're going to need training data for that.
All right, we've got lots to cover here, so let's go through each one of them. But I want to pause here because this is pretty cool. This is Fourier bot here on the top in the front right. We spoke to Zen Ko, one of the presidents. Right in the middle, that's Digit Agility. We'll be doing an interview with their CEO shortly. And on the back left, that is Aptronic, which we're scheduled to do an interview with them as well. And then way in the back there, that is GR1, right? That's no,
H1. That's the H1 from Unitree. GR1 is Unitree. The Fourier. The H1.
Okay, gotcha.
Yes,
okay.
Yes. And then there's Figure One. So we're getting confused with all these different bots.
Okay. Digit. This is the
that's
one.
Unitree H1.
Okay.
And it was interesting to see them all in the same shot.
Yeah. All right. So this is a yet more digital simulation where they're just in a computer, but it looks like from this video that each of the bot, right? They're all different from each other, but they're training all of them in the same simulated world, and they can still kind of like, figure out how to learn how to walk in that real world.
That's very important. And it's like, they may all look, oh, you're just learning how to have humanoids walk, but each of them is going to walk differently because, as we can see, Digit has a very different set of legs, which it's a digitigrade as opposed to a plantigrade. Also the servos, the way everything's actuated is done differently. That all has to be part of that model. So it's not like you're just doing some simple animations in there and putting a different skin on there to show the agility bot going around, the Aptronic bot or Figure or GR1. No, they are modeled down to the details of how the joints are actuated, the masses, everything. Otherwise, you're not really getting much of value out of it. You're not really training it to walk. You need to make sure that your data is really rich and correct. And that way you could also teach it balance in awkward positions, in awkward environments, like we saw steps and uneven surfaces, and also the possibility, even getting bumped into, notice one bot bumped into the other and, it fell over, and enough of that, it will learn how to recover. So hopefully you don't have to go out there and start pushing the bots over or hitting them with sticks or anything like that, but just actually allow them to learn balance control on their own.
Okay. And then the next thing here, that was simulated digital twins in the real world. Now we're talking about teleoperation. So let's watch a little bit of this and you can explain what's going on here.
So again, you've got an operator who's through the glasses is able to see exactly what the bot is seeing from its own point of view, and then using the hand controllers there to move the bot around. So the tracking of that data is mathematically used to convert it into whatever the joint values are of the bot. And of course, because the operator is able to see the bot's actual hands, it's able to see when it's grabbing a glass and tell it to close the fingers, etc. And then that is used again to start building a training set that you can then go and iterate on also in simulation. So you could take the teleoperated data and also put that into a virtual world and start training on that more and more.
Okay. So this guy's teleoperating, and then the bot is following exactly what he's doing. And then, so this is teleoperating to the left. So some humans doing it, but then on the right, they let it go and it can do it autonomously. And then right after this is done, then the very next thing, that drummer, that is no longer teleoperated. This is now a video, right? This bot, the video camera is watching this human do these moves, and then the bot then copies it, not through teleoperation. They're watching the video, correct? Correct. From that, and then being able to infer what it is that the bot has to do. Let's watch a little bit of it. Yeah.
A robot powered by Groot can learn generalized skills like coordination and dexterity that can be applied to a variety of helpful tasks. And emulate human movement just by observing us.
Just by observing. So just by video,
This is made possible with NVIDIA'S technologies that can understand humans from videos, train models in simulation, and ultimately deploy them directly to physical robots, connecting the Groot model to a...
Now, what could be different between the two is that in one case, the bot might only care about the fact that you want to have the drumsticks hit the drums. So that might be the thing. That's the task. The task is that this drumstick is supposed to hit this cymbal, because we're watching that. We're not really watching what the drummer is doing. We're not doing the exact same kinematic movement of the drummer. So you see there's no kinematic overlay in the drummer. It's probably more or less like the task is having those things hit. Whereas in the next one, the idea is that we want to do exactly what the human is doing. So there's now a kinematic model for the motion of the human, and let's emulate that. So it's kind of a subtle difference between the two. It almost seems like, well, they were probably just showing the movements of the drummer, right? It's like, no, they were actually showing the movements of the drumsticks. And now it was up to making sure the drumsticks do the task that they're supposed to do. So again, it would come down to, if you have an operation that like, the coffee maker example, where you're picking up the cups and putting it in, that's the task. That's what you're teaching them. You're not teaching them the movement of the human. The robot is now saying, oh, what I'm supposed to do is pick this thing up from over there and place it in there. sometimes the movement of the human can be used as a hint on what to do, but you're not actually trying to do exactly the human motion. You're trying to achieve a particular goal. So with the drumsticks, depending upon the size of the drummer, if you were to be looking at exactly the movement of the drummer, then the robot may miss the cymbal completely. So the idea is like the task is go ahead and make sure the drumstick hits this particular drum, and you're not doing, air drumming or air guitaring or something like that, but actually hitting it. So that's the subtle difference between emulating the movement of a person and actually accomplishing a particular task.
It's very interesting, actually, now that you explained it, because even the drum example is very complicated, right? Because it's not just moving my hands. It's actually, I'm using a tool.
Yes.
And that tool is going to hit something, and it's going to, how drumsticks are, right? It kind of like, wiggles. If you hit it harder than less harder, it can actually, if you hit it hard enough, it's going to fly off your hands. Yeah. It needed to know how to use a tool to play the game, the drums. That's amazing.
And see, that's important, because if it comes down to just emulating the human motion, and if you've got a bot that isn't exactly like that human, you can't copy that motion one-to-one.
No.
So
my hands are different than their hands.
So think about, a teacher up on the chalkboard is going to be teaching the students how to draw a certain letter, and you're just trying to figure out how to get that shape. You may look at the movement that the teacher is doing to get a hint, but some people will hold the chalk differently or their pen differently or something like that. So what's important is the task, and the task is go ahead and draw a circle, and not look at whether the elbow is out this way or that way, or whether I'm doing it left-handed or right-handed or anything like that. That doesn't matter. What you want to do is figure out what the task is. And so all that training data starts coming in there, and it starts to kind of combine, and that we don't think about it. A lot of times when we watch what someone does, are we actually observing their movement, or are we actually observing what they do? And, sometimes you have to get down to it. You'll look at, good coaches will be looking at the movement that an athlete is doing, make a recommendation. Oh, this is what you have to do to be a little bit better in performing. Swim coaches will be like that. They'll be going there and they'll make a little suggestion. Oh, your shoulder movement has to be a little bit better. Your elbow has to come up, and we want you to do this when you're coming on in. And they'll be like, that subtle little thing, which is very different than you just kind of watching someone splashing the water and you were trying to do the same thing. So there's 2 degrees of that are going to be in there. And of course, what's happening when they are running the simulations is that internally, when it optimizes, it's trying to figure out, well, how do I do this task with the arm that I have? That's the most efficient way. And eventually it'll figure it out. And that's why you're going kind of in both directions.
Okay, let's watch the next bit, because this part here is actually large language model where you can speak to it. And
by following natural language instructions.
Hi, GL1. Can you give me a high five?
Sure thing. Let's high five.
Can you give us some cool moves?
So let's say, not only did he speak to it, and it, of course, knew how to reply back, it knew what he meant by high five, and then it actually did the high five. That's what they're trying to say here, right?
Right. In some cases, you can be very direct. I want you to do this specific thing. It knows what a high five is. Okay, cool moves. Well, was it actually taught that, doing a dap is a cool move, and it's doing exactly that, and that's what it's called, cool moves? Or has it been taught a bunch of things where they keep on telling it, hey, that's a cool move, that's a cool move, show me something. So it's no different than, asking Grok to give me a dad joke. Okay. Yeah. It's not that you've taught it one dad joke. It knows, there's this category of dad jokes over here. I'm just going to pick one out of it. So it probably picked out a category of cool moves that it just felt, hey, this is kind of for the mood that we're doing right now. And it may have done something else. Yeah. So some cases you can be specific. Some cases you can be very vague. The large language model will make that choice for you, because it's building this really rich, if you want to think of it, token library, but more or less it's an action library of all kinds of actions. And the language model is picking which action you want to do. So which joke do you want to tell right now? And you kind of read the mood of what's going on. This is the one I'm going to do. I'm going to pull it out of my library. And now it's just motion tasks that is going in. And if it learns enough of these motion tasks, it'll just be able to figure out what it is that you need to do at that particular time.
Scott, I'm very concerned that if you're near one of these bots, the bot's going to do something very dangerous, because you're going to say something
all the hand waving
that's very logical to you. No, it's going to be something like very logical to you. And then the bot goes, okay, you want me to, I don't know, slap the baby or something, whatever, like these terminology. And then it's like, okay, you want me to do that? Oh my God. Okay. This is so cool.
Sure. Check this out.
With Isaac Lab, Osmo, and Groot, we're providing the building blocks for the future of AI-powered robotics.
with the Easter egg of the last robot being four-wheeled.
Right. The last robot's a four-wheeled truck. But that's obviously what Tesla says, right? Elon has been saying that we have 5.5 million robots already today. There's no one this many robots because every robot just happens to have, the car just happens to have four wheels. But it actually can recognize, it can read signs, it knows what it needs to do based on the environment. It's figuring things out. It's real world AI. So what we saw here was transferring simulation and, training data and then putting it to real world. We're all excited. But Tesla's been doing this already.
Yeah, but now let's kind of look at the analogy, because we've all understood how full self-driving has been evolving. And the idea is that you needed real world data versus these really limited data sets. They were doing a lot of simulations of autonomous driving. A lot of the other companies were doing that, and they would be doing it on test tracks and in very limited circumstances and only getting so far. And Tesla was the only one that had the foresight. It's like, no, we're putting cameras on all our cars and we just need to get the data, because the data is where you were able to solve this problem. So that's given them a huge advantage. The other thing is that Tesla's AI division has not been trying to solve artificial intelligence by scanning the internet for language and coming up with a large language model. They've figured out how to actually bring in video data, and from video data, train the car what to do. Basically the same thing that these bots are doing here now. And that's why, they already saw, hey, we've got something here. We could probably train something other than a four-wheeled robot, but maybe a four-armed robot will be able to do it. So that means Tesla already has a capability, and that's why they don't need to be in that group of 9 robot vendors out there, because they already have their own solution. Where they may be coming up a little bit short is in the area of the large language model, but it shouldn't be that hard because there's so many of them out there. And of course, Grok just was made available over the week. And, that will probably, we're pretty sure, is going to be the large language model interface. Now, the large language model interface that you need for these bots does not have to be super, super sophisticated. It just has to understand language. And so Grok is probably more than efficient enough to be able to do it. In many cases, it can probably be a scaled down value, because you just have to make sure to understand some things. It's like, it's not like the robots have to be able to speak to you in the voice of Shakespeare or something like that, or start doing sonnets or something like that. That's all going to be nice. And it's nice that they have cultural references that you can be very vague, and rather than giving the color, give it like a little game that you say, what's the color of Darth Vader's sword? Use that for your box. That won't be hard. That's going to be in the training set for whatever language model it is in there. The question is what's going to be sufficient for being able to do these particular kinds of tasks. And now so comes the other questions, that if the key to the success for full self-driving has been like driving all over the place, everywhere in the world, what is it going to be for these robots? Are they just going to stay in the lab and do that? How do we get them out and get a bit more? And, the early days, probably they won't be wandering about too much too early, because the focus is going to be getting them in the factories, getting them to do useful work, getting them to be able to pay for themselves and pay for the bills so we can do that. Because that's okay. I mean, it's like the idea of full self-driving, driving all day around the test track. You don't make money doing that. You maybe can prove it can drive safely and stuff like that. And everyone's like really excited. It's like, well, when are you going to let it drive in the real world? It's like, well, we're not sure if it's ready yet for that, but it's not making money when it's doing that. When it's walking around inside the factory doing work, it's making money. Okay. At that point, till you get to the point that you are really satisfied with the capabilities, that you think, okay, we can have a much wider kind of training set we can go on. Now, the question is, and this is something Warren Redlich has brought up a couple of times. I think he's not too far off the mark. Maybe he's right on this, and that we think these bots are really just going to be leased for a while and really kept in the factory. But why not have like an Optimus beta test program where people voluntarily, will pay to have the Optimus come into their houses voluntarily and just start doing stuff in houses all over the world in different environments. You got to pick the people right. And maybe that's the way you do it. So if we want to look at full self-driving as an analog on how you might be able to get to that stage, that's possible. I mean, that could happen. Others going, I'm not predicting that it is, but and so I'm giving credit to Warren. So if it turns out to be wrong, I can blame him.
Sure. Yeah.
Okay.
All right. So I mean, it's clear now that you need to get as many bots created. You need to have them in the real world, and then they can all feed and learn from each other as well. That's why I think NVIDIA is doing what they're doing, right? They convinced these 9 partners and more. Listen, the more we are, because we know that each one of them, one of their biggest weaknesses is they aren't able to scale up and manufacture the numbers. Tesla can do it, and they'll have so many of these out there, and they will learn quicker. Just like that's their advantage with FSD and autopilot or autonomy in cars. And these guys are together. They're going to do this. So
yeah,
they need to have as many. Yeah.
And I hadn't thought of it that way, but that could be really interesting on whether you could take like the agility bot and teach it a bunch of tasks and get it to that point,
sure.
and then suddenly transfer it over to Apptronics, and it suddenly figures it out. Even though they're kinematically very different, that somehow you've got some combinations in there, which means they don't have to produce 100 or 1,000 bots themselves. They just have to have 1,000 bots in the collection, in the collective, in the board collective, if you want to think of it that way, and that they may be able to use that as a leverage. I hadn't really thought of it that way. It's possible. I mean, the tricky bit is the fact that they are, really different mechanically and how you kind of solve that issue. But it may be that you get enough kind of refinement, you get close enough to that one shot. Because the reason you go in the real world is that the physics is a little bit different. The way you model the actuators is not quite accurate enough, or it's not behaving the way you expect it to. The fact that objects actually have different friction and everything else. And that may be something that one of them picks it up and is able to transfer to the others, or maybe not, because just the way it senses the grasping, what the forces are to pick up this bottle may be very different for one hand than it is for another. And you may not be able to transfer it from one another. But we could be wrong. It may be that no, actually they know how to do the mapping from one to another. And I bet that's something that they're working on, that you would be able to deploy a task that you taught on one of these bots over to another one, even though it's never seen that task before. And that could be exciting.
Exciting. Okay, let's show 1X Technologies. And so we've got here a demo from 1X. As we predicted, yesterday, as soon as the demo or the Jensen Huang NVIDIA keynote happened, then we had Digit drop a video, we had Apptronic drop a video, and so this is 1X. 1X is a Norway company. We're looking at their Eve version of their bot that has wheels on it. Then they've created a Neo version that's going to be humanoid with hands and actual feet. And then so what they said was 1X mission is to create an abundant supply of physical labor through androids that work alongside humans. We're excited to share our latest progress on teaching Eve's general purpose skills. The video we're going to watch is autonomous. It's all 1X speed, all controlled with a single set of neural network weights. And then Bernd, I spoke to him. He's the CEO founder of 1X Tech. By the way, 1X is actually partnered not only with NVIDIA, but also OpenAI. So there's going to be something very similar to what we saw with Figure partnerships, both of those companies as well. So he said this: latest software update with contact-rich manipulation skills and general picking. With all capabilities merged into a single set of goal-conditioned network weights, we see first signs of zero-shot behavior, and you explain what that is.
Yeah, that means, they simulate it once, and then it works the first time out.
Let's go ahead and watch the video.
Don't have to do any retraining.
Yeah. So why don't you speak over it and tell us what we're seeing.
So again, notice that everyone's using like the same format of saying, hey, this is end-to-end autonomy, and this is our March update. So we're going to be seeing more of them using the same thing. And again, he talked about contact rich, where there's obviously a lot of manipulation needing to capture a lot of different things, understanding how the different doors and drawers are going to be working. And so it's familiar with this kitchen. Now you notice it's its own kitchen. It's not the same kitchen that Digit and Apollo were using yesterday. Another task of some flexible items that we've seen here. And again, this is Eve, which is their first generation, which is wheeled and has very simple hands. Yet even with these very simple hands, it folds a t-shirt about as well as I do. I mean, I'm tolerant of that. They don't have to be that perfect. I just want to make sure they kind of fit in the drawer or in the luggage if I have to go somewhere. So, I mean, that's adequate for the most part. And then you'll see that there's manipulation here of, I'm not sure, it looks like there's a gesture. From that gesture, it realizes, oh, you want me to hand this to you. So I'm not even sure if anything was spoken or if I needed to do it. Now, we all know this when we get our Amazon packages, that usually not only is there something inside the box, but there's also a little bit of packing material. And so it's learning how to close the box, which we all know can be a challenge, especially around Christmas time. And then we have it coming in here and putting some of the packaging material in there. So if you ever wondered how that was done, that's how it's done. So you have these suspensors that are out there on the line. And of course, this is something that is done all around the world and in all these different logistics centers, where boxes had to be put in the boxes and packed up, and a little bit of packing material. So you are seeing the first signs of what will be probably some of the first activities, useful work that Eve may end up doing in a logistics center somewhere in Norway or elsewhere in Europe or anywhere else in the world. And again, showing the different strategies to pick up different objects because it's being trained on different objects. Look at what it has to do to pick up the sponge. It uses something that's a little bit different. I wasn't expecting that, but that's one way to do it. And again, very simple pincer grippers are able to do a variety of tasks, even though they are not a 5-digit hand.
So this part here is the part that I was very, very excited about, which is oops, I just had it all set up and ready to go. The part where he's manipulating the box, but you see how he can actually control the flaps of the box. That, we've seen, of course, many bots doing pick and place, grab a box, move it, grab a box, move it. But this is like, look, I don't know. They're saying this is autonomy, right? There's not teleoperating.
Yes.
This is now autonomous. So
end-to-end autonomy, one world neural net that I talked about. So there's nothing in the middle. It's photons in, actions out.
So for them to actually, for the bot to not only recognize as a box, but also to now recognize that there's flaps, and I need to put the flaps like this.
Crazy.
This is the part that blew me away. I'm like,
and especially if they're doing a lot of this one shot, it's just amazing.
Yeah.
Now, I've had to do simulations like that all the time in our software with, industrial bots and stuff like that. And yeah, it's a tricky animation to get together. And now to actually see something in the real world, go ahead and do that. I find that absolutely remarkable without any training except demonstrations.
All right. Wow. So that one was interesting, but of course it's not as impressive as the others because it didn't have the hands and the feet yet, but they're creating Neo. Neo will be the full humanoid. We saw it, what it looks like.
But
then
forget the mechanics. The thing is, we're seeing everyone is able to do this end to end and they're able to get results really quickly. And I'm not sure to be excited or scared because what that means is that everyone's being able to converge to it. There's a solution out there. They're all just getting better and better. It's a matter of more and more training data. And the mechanics will come. And again, remember, Brett said back in the fall, it's like, oh my goodness, I thought the AI was going to be the one that takes forever and that the hardware would be ready before. And now it looks like it's the other way around. And I agreed with him at that point that, the hardware will be ready before the AI. I wasn't sure if I could agree with him this flipped around because I wasn't seeing what he was seeing. I'm now seeing what he's been seeing and I understand. It's coming really quick.
It's coming quick.
Which I think is why they're moving probably to their Neo model because they begin to realize that, wow, this is just going so fast. We may as well go, get the thing to start walking and let's put real hands on it and everything. We've got a design. Let's go ahead and start working on it because the hardware now needs to catch up.
So they've already proven many times, as you saw NVIDIA doing it, simulation can train to autonomy, teleoperation can train to autonomy, and then just videos can train to autonomy, just watching it and then it can do all sorts of activities. And so it then becomes like, it's like how fast can you train something, useful work? And then the catch up now is how fast can you make these bots? And they don't want to mass produce the bots until they're pretty sure about the low cost of an actuator. They don't have to redesign these things. And so that's sort of where they're just all racing now to build the final design of some of these bots. So at least make a couple thousand. And so, we're here. Maybe next year we'll see 1,000 bots.
Yeah. Scaling, all of them are going to start scaling pretty quick. And I'm sure they're putting their teams together right now to look at how that can be done or to find partners. They're all having to do some production. They may already have some partners for certain key components. I'm not sure where some of their actuators are coming, whether some of them are just, still building them in house, in which case it may be slow, or they've been able to partner with someone that has experience in being able to mass produce motors or actuators at the scale that they need. Things are definitely moving quick. And I think the one thing you can see as far as all the different ways of training, from demonstration to teleoperation, to the point that, think about the ideal training scenario is that we read a book about how to do something. So theoretically, we understand how to do it. Usually that means we have to go out and practice what's there. But imagine you can just read a book about it and the next day you can go out there and actually do it. So, I read a book on how to play the violin and suddenly tomorrow I'm a concert master. Yeah, it doesn't quite work that way, does it? But it seems that they're getting closer to that. And that's almost what this one shot is like, is that they sit down, they do it in the simulation, and think about it. It's almost like you kind of learn about something during the day, but you're not sure about it. And then you sleep on it. And then while you're dreaming, your body is like somehow figuring out how to accomplish that task. And the next day you get up and like, wow, I can do it all of a sudden. Yeah. That's what's going on in the simulations. It's basically putting it into like this dream state, checking everything out, and then it finally understands, and then it wakes up and like, oh yeah, I got this, as if it had done it 1,000 times before, because it had done it 1,000 times before in its head.
Yeah. You know, it's funny, right? So of course, as these demos drop, everybody continues to complain saying, hey, this is all faked. It's not true. And of course, when Figure dropped theirs, first reaction by everybody was, this is all scam, it's fraud. And, you know, but when you see NVIDIA doing it, how many people here are saying that's a scam, that's a fraud? NVIDIA is part of are they part of the whole scam as well? They're all faking all this out? I don't think so. And especially when you have all these diverse group of very intelligent machine learning software developers all over the place, right? We've reported grad students from Stanford. We've reported all these papers that you read, Google, DeepMind, Microsoft, everybody's showing what they can do. It really is like AI. It's like scaring people. Well, now humanoid bots, this isn't fake, guys. This is real.
Yes.
A lot of it's real.
And the thing is, a lot of things that you're seeing are being shown because of the practicality of what has to be done to get the data out. And someone might like, wait a minute, that doesn't look quite right. What's going on here? It's the production quality that sometimes you have to put them out. They are actually doing these things. And, you know, one thing with the presentation yesterday is that it wasn't obvious right away. It was obvious to everyone sitting in the audience that the 9 bots that were up there were actually projections on the back of the wall, and they weren't actually there. However, we know that those bots actually do exist, and they have been together in the same lab, because we then saw a video after that. It's just impractical to get them out there on the stage at the same time for just a couple of minutes. So that is showing, yes, so you could see right there, yes, those bots, the real bots weren't there, but the real bots do exist, and the real bots are being used in these different labs, and we've already seen that. How many do we count there? At least 4 of them together in that one shot.
Well, there's 9 of them, right? And then
there's 9 there.
We thought that they were real, but they're not. They're actually what do you call it?
Because that's how good NVIDIA projections are,
right?
You know, if you're not at the right angle,
watch this. There, you can see that it was just a screen.
Exactly.
It was just a screen.
So anyone in the audience knew that it wasn't the real one. The point is that this is who they're partnering with, and we can see that they really have been partnering with these bots, and these bots really are accomplishing real tasks. So just want to bring that up, because if anyone sees that and tries to seize that and says, see, it wasn't real, it was all staged. It's like, okay, it's just for the practicality of doing it. Is it really worth the cost and expense for like the 2 minutes of having the real bots out there when they don't have enough models of them out there right now? They're trying to do real work. They really can't tie it up for a week to send it out to California and get it set up and make sure it then comes back like it's supposed to. So eventually they're going to be out there on the stage, and they're going to all walk up, and they're all going to shake Jensen's hand. That, you know, if not next year, the year after that.
Next year for sure. All right. Thank you so much, Scott. Appreciate this. That was great breakdown, and we just keep getting it every single day. Thank you, everybody. Follow Scott also at Going Ballistic 5 on Next, and he's on this channel and many others quite often. See you guys soon. Thanks, everybody.
Okay.
Bye.
Bye, Herbert.
I've created a website that is the most comprehensive resource for the Tesla investor. Please check it out. Simply go to my website at herbertong.com.